Good afternoon. This is Mechanics of Materials. And we are in the fifth edition of the statics textbook. Author is R.C. Hibbler. So we're working our way, and we're in chapter 10 now. It's on page 452 of the text. And here we'll cover the topic of torsion. So this brings us back to a statics concept of torque. And we define this as a moment that tends to twist a member about its longitudinal axes. And we are considering this in the design of drive shafts, we'll say that are used in machinery. So we're concerned with the stress and deformation that occurs in a shaft when it is subjected to torsional loads. And throughout this chapter, we were mainly concerned with circular shafts as they support the most as far as rotation, circular shafts. So if a circular shaft is fixed at one end, and a torque is applied to the other end, this will lead to angle of twist and it's basically how much distortion has occurred in the circular shaft due to the applied external torque. So if we look at the cross section of a circular rod, the shear strain within the shaft varies linearly along any radial line from 0 at the center to a maximum at the outer boundary. So our shear strain, if this is the center of the circular shaft, it varies linearly from the center out to the radially, so along the radius, out to a maximum value at the outer surface. So this would be the maximum shear strain, and this would be where shear strain is 0. So then, as it varies along its length, we can determine your shear strain as a function of the distance from the center of the circular shaft. So we'll define a term. As you go out from the center of the shaft to the outer surface, the maximum distance is C, the radius. First page. Radius C is maximum distance from center of circular shaft to the outer boundary. However, like we said, we can determine the shear strain at any radial distance extending from the center. So we'll define the term rho as the evaluated radial distance in question. So by inspection or logically, maximum rho is this radius, C. And like we said, your maximum shear strain is at the outer boundary and is 0 at the center. So the shear strain is caused by the external torque. We can define that as your shear strain is the ratio of your radial distance in question over the radius, which is maximum rho, C is maximum rho, so rho over C times your maximum shear strain. This is valid because there's a linear relationship between the shear strain and the distance from the center. So working then towards the torsion formula, and applied external torque to a shaft creates a corresponding internal torque within the shaft. So as our antennas should go up, whenever we see the term internal, we know we have to do some method of sections work. So here we're going to relate the internal torque to the shear stress that acts on the shaft's cross section. So if we assume material is elastic and we're working in the elastic region, then Hooke's law applies for our shear stress, shear strain relationship, and therefore our maximum shear stress and just like our shear strain was 0 at the center of the shaft and a maximum at the outer boundary at a distance C from the center, our shear stress varies the same way. Our shear stress is a maximum at the distance C from the center, and it's 0 at the center of the shaft. So likewise, our shear stress is the ratio of the radial distance in question, rho, over the maximum radial distance, C, which is the radius, times the maximum shear stress. This implies a linear relationship. So as we're working towards our torsion formulas, we have to define one more term, J, which is the polar moment of inertia. Of the cross-sectional area. So if a circular shaft has a solid cross-sectional area, then the polar moment of inertia, J, is defined as pi over 2 times the radius to the 4, the radius c to the 4th power. This is for a solid circular shaft. If the shaft is hollow, so like a tube, then J is defined as pi over 2 times the 4th power of the outer radius minus the 4th power of the inner radius. So J is a positive quantity, and it has units of, say, length to the 4th power. So this could be inches to the 4, or say millimeters to the 4th power. So then coming back to our torsion formulas, so the maximum shear stress in a shaft, which occurs at outer surface, so this is maximum shear stress, is your internal torque, T, times your outer radius of the shaft, C, over your polar moment of inertia. T is your internal torque. C is your outer radius, and your J is your polar moment of inertia. Therefore, it follows that if your maximum shear stress, which we already said occurs at the outer surface, that we can find the shear stress in the shaft at any distance extending from the center, which would be a function of rho. And these are your torsion formulas. And these are to be used only on shafts of circular cross sections, and the material is homogeneous and behaves in a linear elastic manner. And let's talk about power transmission. So shafts, as we said, are often used to transmit power developed by machines. Therefore, they are subjected to torque that depends on both the power generated and the angular speed of the shaft. So power equals work per time. Also, the work transmitted by rotating shaft equals torque times the angle of rotation so power is equal to the applied torque times the angular velocity, and this is omega, so power, we said, is work per unit time and in SI units it is expressed units of watts. This is SI units. And 1 watt equals 1 Newton meter per second. Omega, the angular velocity, is measured in radians per second. Remember, this is angular velocity. In US units, power foot-pound force per second. However, we use the term horsepower in US units, where 1 horsepower is 550 foot-pound force per second. So another term to define the frequency of a shaft's rotation, this is F. And this is the measure of the number of rotations the shaft makes per second. And expressed in units of hertz, 1 hertz is equal to 1 cycle per second. And we know from our geometry that pi radians equals 180 degrees. So 2 pi radians equals 360 degrees, a complete circular revolution. So therefore, 1 cycle is equal to 2 pi radians, which is 360 degrees, a complete circle, complete rotation. Therefore, we can redefine our angular velocity, omega, as 2 pi times f, the frequency. And then we can rewrite our power equation from the torque times the angular velocity. We can rewrite it as 2 pi times the torque, 2 pi f times the torque. So let's get into some problems so we can get some practical understanding of what problems we will be solving with these formulas. So let's take a look at problem 10-3. This is on page 469 of your text. Here we have a aluminum shaft and its allowable shear stress equals 100 megapascals. So we see the word allow, we know that's synonymous with our maximum shear stress. 100 megapascals. Convert our units. This is mega, 10 to the 6 pascals, Newton per meter squared, just so we can be clear on what we're saying. The diameter of the shaft is 100 millimeters. Diameter is 100 millimeters. All the formulas we defined to date is in radius terms. So then our C would be 100 millimeters over 2, our radius. So that's 50 millimeters, which is 0.05 meters. They want us to determine the maximum torque that can be transmitted. The maximum torque. Okay. So here we're going to apply our torsion formula, which we already said was T max. This is formula, our torsion formula we defined. This is on page 457 in your text. Our maximum shear stress is T times C over J. And we were given our maximum shear stress as 100 times 10 to the 6 newtons per meter squared equals to T, which is what we're in search of, times our C, which we said is 0.05 meters. We're getting everything in the correct units, over our J. Now, we said for a solid circular shaft, J from our equation is pi over 2 times C to the 4. So plugging that into here, our J will be pi over 2, our C being 0.05 meters to the 4th power. So now we just have to plug this into our calculators and solve for our one unknown T. So then our torque here comes out to be 19.63 times 10 to the 3 Newton meters. We can write that as 19.6 kilonewton meters. So that's our maximum torque for this configuration. A part B to the problem asks what would be the maximum torque if a 75 millimeter diameter hole was bored through the shaft. So now it went from a solid shaft to a tubular shaft. So we know then our polar moment of inertia, J, will change. So once again, our maximum shear stress has not changed. But our J will change. So once again, we were given our maximum shear stress as 100 times 10 to the 6 newtons per meter squared. Always be careful to make sure you're using the correct units so that your math comes out correctly. Units matter. Times your T times your C, the maximum radial distance, the outer radius, which is 0.05 meters. But our J now is different. So for tubular, J, our polar moment of inertia, is pi over 2 times the difference of the outer diameter to the 4th power and the outer radius to the 4th power minus the inner radius to the 4th power. So plugging that formula into here in the denominator is pi over 2 times our outer radius, which is 0.05 meters, minus the inner radius. And the inner radius corresponds to the inner diameter of 75 millimeters. So the inner radius, which would be our 75 millimeters over 2. And this corresponds in meters as 0.0375 meters, or 37.5 millimeters. So plugging that back into our equation, 0.05 meters to the 4 minus our 0.0375 meters to the 4th power and plug them into our calculators and solve them for T, you get your torque for the hollow shaft to be 13.4 kilonewtons per meter. And this is for the hollow shaft. So as it corresponds to our solid shaft, the torque was 19.6 kilonewton meters. So obviously this kind of makes sense intuitively. A solid shaft can withstand a higher torque than the internal. Than the tubular hollow shaft. Let's take a look at another problem. Problem 10.4, same page. Here we have a copper pipe, and it's tubular because they give us an outer and an inner diameter. So our outer diameter, DO, is 40 millimeters. So then our outer radius, CO, is 20 millimeters, or 0.02 meters. The inner diameter is 37 millimeters. So our inner radius is 18.5 millimeters, which is 0.0185 meters. And the pipe is subjected to the three torques. And they want to know the maximum shear stress. So to use our torsion formulas, we have to know the internal torque here, and the maximum shear stress will correspond to the maximum internal torque experienced by this shaft. So then, if we work through it, start with our free body diagrams of each segment where there's a different torque. So we look at this first segment, where we make our section. It's subjected to a clockwise torque of 80 newton meters. So the sum of our moments for equilibrium have to equal to 0. Then the torque we'll label T1 here has to be 80 newton meters and in the opposite direction. So then we move on to the next section along the shaft. We have the 80 newton meters as before. Well, there's a opposite applied torque, external torque of 20 newton meters. So then to find the resultant internal torque here, once again, the sum of our moments equals 0. Then to balance this out, we'll label it T2. This would be, let's do it a little better. 20 newton meters minus 80 newton meters. And we'll say plus T1 equals 0. So T1 is 60, I'm sorry, T2. This will be T2. T2 is equal to 60 Newton meters. lastly, for the last section we will have to make, once again, we have that 80 Newton meter applied torque. We have the 20 Newton meter applied torque and another 30 Newton meter applied external torque to the shaft, or the pipe, I should say. So here, this will be our 20 Newton meter minus 80 Newton meters minus 30 Newton meters. And we have to take into account, we're solving for our internal torque in that section. We'll call it T3 plus T3 equals 0. T3 will be 90 Newton meters. We're keeping track of our rotation directions, and they have to all balance out for it to be in equilibrium. So to recount that, we have our T1, we said was 80 Newton meters. Our T2 in the second section was 60 Newton meters, and our T3 was 90 Newton meters. The question is wanting to know the maximum shear stress, and since the torque for the torsion formula, let's bring the formula back up, TC over J, with the torque being in the numerator, multiplying will lead to a larger maximum stress. We need to consider the largest torque, which will be T3, 90 Newton meters. So therefore, our maximum shear stress developed in this copper pipe will be our T3 torque, which is 90 Newton meters, times our C, which is the outer radius of 20 millimeters, which is 0.02 meters, all over our J, and this is a tubular pipe because it has both an outer and an inner diameter. So this is for J, for a tubular pipe, this is pi over 2 times the outer radius to the fourth power minus the inner radius to the fourth power. So our maximum shear stress is 90 Newton meters times 0.02 meters over pi over 2 times your outer radius, which is 0.02 meters to the fourth power. Have to do that. Minus your inner radius, 0.0185 meters to the fourth power. Plug this in and solve. Your maximum shear stress is 26.7 times 10 to the 6 Newton per meter squared, which comes out to 26.7 megapascals. Let's take a look at another problem. Look at problem 10-8. This is page 470 in your text. Here we have a solid 30 millimeter diameter shaft. So this is 30 millimeters. So our C is 15 millimeters, which is equal to 0.015 meters. Is used to transmit the torques applied to the gears, determine the absolute maximum shear stress in the shaft. So this is similar to the problem we just worked. So we have to do our sections to determine our maximum torque in which section of the shaft. So for, we'll say section AC, we have an applied torque of 300 Newton meters. So to balance that out, our T, say AC here, excuse me, for our sum of our moments to equal 0, this would be 300 Newton meters minus TAC equals 0. TAC is equal to 300 Newton meters. So our next section, which would be segment CD, we're trying to find the internal torque. That's why we're doing the sections, method of sections here. We have to take into account this is 300 Newton meters. And a 500 Newton meter applied torque. So then our TCD so this would be TCD minus 500, let's make that a little neater, TCD minus 500 Newton meters plus 300 Newton meters equals 0. TCD is 200 Newton meters. Our last section would be section DB. So you have your 300 Newton meter, your 500 Newton meter applied torque, and your 200 Newton meter applied torque. So then our internal torque at this section, and we'll label it TDB. This would be TDB minus 200 Newton meters minus 500 Newton meters plus 300 Newton meters equals 0. So the torque in this section is equal to 400 Newton meters. Back to our torsion formula. Maximum shear stress will be our maximum torque, C over J. This is a solid shaft. And our maximum torque out of TAC, which is 300 Newton meters, TCD, which is 200 Newton meters, and TDB is 400 Newton meters, will be the 400 Newton meter value. Our radius C of the 30 millimeter shaft is 0.015 meters. And our polar moment of inertia for the solid shaft is pi over 2 times 0.015 meters to the fourth power. Therefore, our maximum shear stress comes out to be 75.5 times 10 to the 6 newtons per meter squared, which is 75.5 megapascals. Let's take a look at another problem. Problem 1026. This is page 473. So here it says we have a pump that operates using a motor. So the power is 85 watts. If the impeller at B is turning at 150 revs per minute, determine the maximum shear stress in the 20 millimeter diameter transmission shaft at A. So and this is, okay, so assume it's a solid shaft. All right, so diameter is 20 millimeters. So our radius then is 10 millimeters, which is 0.01 meters. We said a watt is a Newton meter per second, so 85 watts is equal to 85 Newton meters per second. So now we need to determine our angular velocity. So they gave us the speed is turning in revolutions per minute. So that's 150 revolutions per minute. But we need this value in radians per second for our units to be able to be worked in our standard SI units. So revolutions per minute. So then to get it in radians per second, this is a circular shaft. We said one revolution is 360 degrees, which is 2 pi radians. So 2 pi radians is 1 revolution. So now we have this speed in radians per minute, but now we need to get it in radians per second. So 1 minute is 60 seconds. So angular velocity now in radians per second is 5 pi. And this is radians per second. So then we defined earlier that our power is our torque times our angular velocity. So if we rearrange this equation, our torque is our power over our angular velocity. So torque would be then 85 Newton meters per second over 5 pi radians per second. Divide these terms. Our torque is 5.41 Newton meters. So now to find our maximum shear stress, torque times the outer radius over J, 5.41 Newton meters times our C, which we said was 0.01 meters, over our J, which is pi over 2, times our C to the 4, C being 0.01 meters. So your maximum shear stress is 3.44 times 10 to the 6 newtons per meter squared, which is 3.44 megapascals. So we mentioned the angle of twist earlier. Now we will define the equation or the formula for determining it. So we talk about angle of twist. We want to know that due to applied, the external torques, how one end of a shaft changes, say due to the applied torque, with respect to the other. And we're talking about circular cross sections. Circular shafts. And we're talking about homogeneous and say linearly elastic material. So think about it. If you held a pencil or some material, and if you held one end fixed and you apply the external torque to the other end, it will begin to twist. And we're here now to determine that angle there of twist of the shaft. So the angle of twist is defined by the symbol phi. This is the angle of twist of one end of the shaft with respect to the other. And this is units of radians. You have your T, which is your internal torque. Keyword there, again, is internal. You have your L, which is the length of the shaft. You have your polar moment of inertia. And you have your G, which is your shear modulus of elasticity. So if you're applying this formula to a shaft of constant torque and constant cross-sectional area, the formula is torque times your length of the shaft over your polar moment of inertia times your shear modulus of elasticity. This is for constant torque and constant cross-sectional area. But if the shaft is subjected to multiple torques, or the cross-sectional area changes, or the shear modulus or the material changes, so then you have to compute this for each segment that is the same. So take a look at the problem. Let's look at problem 1035. This is on page 483. It says the propellers of a ship are connected to an A36 steel shaft. The length is 60 meters. It has an outer diameter of 340 millimeters. So our outer radius is 170 millimeters, which is 0.17 meters. And has an inner diameter of 260 millimeters. So our inner radius is 130 millimeters, 0.13 meters. The power is 4.5 megawatts. Which mega means 10 to the 6. This is 4.5 times 10 to the 6 Newton meters per second. And the shaft rotates at 20 radians per second. They want us to determine the maximum torsional stress in the shaft and its angle of twist. So our first step is going to the back cover to get our G value. This is in SI units. So for A36 steel, go into our back cover. The G value for A36 steel is 75 gigapascals. Which is 75 times 10 to the 9 Newton per meter squared. Giga, 10 to the 9. So now we can get to work. So we know the formula power is the torque times angular velocity. Rearranging that to solve for our torque. Torque is our power over our angular velocity. Power we said is 4.5 times 10 to the 6 Newton meters per second over our angular velocity, which is 20 radians per second. So our torque is 225 times 10 to the 3 Newton meters. So then our maximum shear stress will be our torque, which is 225 times 10 to the 3 Newton meters, times our outer diameter, C, which we said was 0.17 meters, times our J. This has both an outer and an inner diameter, so it was a hollow tube. So this would be pi over 2 times your outer diameter to the 4, which we already determined was 0.17 meters, minus your inner diameter, which is 0.13 meters. Plug this into your calculator and solve. Your maximum shear stress is 44.3 megapascals. So now for the angle of twist, phi is your torque times your length over your polar moment of inertia times your modulus of rigidity. So our torque we determined was 225 times 10 to the 3 Newton meters. The length here is 60 meters. Our polar moment of inertia, we said, was pi over 2 times 0.17 meters to the 4 minus 0.13 meters to the 4 times our G, which we grabbed from the back cover of the book, 75 gigapascals. So that's 10 to the 9 newtons per meter squared. Remember, we have to convert our unit so everything works out. This comes out to be 0.2085 radians. If you want to convert that to degrees, it's approximately, well, 0.2085 radians times 180 degrees is pi radians. We get about 11.95 degrees is the angle of twist. Let's take a look at another problem. Take a look at problem 10-51. This is on page 485 in your text. So here we have a device that is used to mix soils in situ stabilization. If the mixture is connected to an A36 steel tubular shaft, that has an inner diameter of 3 inches. So the inner diameter 3 inches. We're in US units. So our inner radius is 1.5 inches, has an outer diameter of 4.5 inches. So our outer radius is 2.25 inches. So they want the angle of twist of the shaft at A relative to C. All right, so here we have to use, we're subject to two different torques, so we have to use our summation formula here of your torques times your length, polar moment of inertia, and your modulus of rigidity. So now we have to find our internal torques here. So then I'll draw it to an angle. For your segment AB, you have a torque of 5,000 pound-force feet. So then we have to have a balancing here of our torque in segment AB. So TAB minus 5,000 pound-force feet equals 0. So TAB is 5,000 pound-force feet. So then for segment B, this is segment or section AB. So then for section BC, you have your 5,000 pound-force feet applied torque here, and you have a 3,000 pound-force foot torque there. So then our internal torque in section BC TBC minus 5,000 pound-force feet minus 3,000 pound-force feet. The torque in section BC is equal to 8,000 pound-force feet. So throughout the tube, the material is still A36. So our G value is the same, but since our torques change into two different sections, we have to use the summation formula. So our angle of twist of A relative to C will be our torque in section AB times your length of section AB over J times G plus your torque in section BC times your length of section BC over JG. So we are in US units this time for A36 steel. So we go to the back cover. Our value for G for US for A36 steel is 11 times 10 to the 3 kilopounds per square inch, KSI. So this is 11 times 10 to the 3 times 10 to the 3 pound force per inch squared. Kilopounds per square inch, KSI. Always convert your units out so that your math works out. So the angle twist of A with respect to C, so our torque in section AB, we said was 5,000 pound force feet times 12 inches, 1 foot, times the length of AB, which is 15 feet, times 12 inches, 1 foot, converting from feet to inches, over our J. This is a hollow tube, so it's the outer radius to the 4th power, which is 2.25 inches, minus your inner radius, which is 1.5 inches, to the 4th power, times your G, which we said is 11 times 10 to the 6 pound force per inches squared, plus our TBC component, which would be 8,000 pound force feet. Convert that feet to inches, 12 inches, 1 foot, times your length of segment BC, which is 20 feet, times 12 inches, 1 foot, over your polar moment of inertia, which is your outer radius, minus your inner radius, times your G. Our units are all in the same pound force and inches. So angle of twist, A respect to C, is equal to 0.0952 radians. If what that in degrees, we know 180 degrees is pi radians. So this comes out to be approximately 5.45 degrees as your angle of twist. So we have to talk about statically indeterminate torque loaded members. So a torsionally loaded shaft will be statically indeterminate if the moment equation of equilibrium applied about the axes of the shaft is not adequate to determine the unknown torques acting on the shaft. So here, just like in the previous chapter, we have to come up with a compatibility equation or compatibility condition. For example, if the ends are fixed, a compatibility condition will require, we'll say if ends are fixed, a compatibility would require that the angle of twist of one end of the shaft with respect to the other to be equal to 0. This is an example of a compatibility equation for fixed end supports. So let's take a look at the problem. Let's look at problem 10-64 on page 492. So we have a steel shaft made of two segments, AC. So we'll say segment AC has a diameter of 0.5 inches. And segment CD, the diameter is 1 inch. If the shaft is fixed at its ends A and B, and subjected to the torque shown of 500 pound-force feet, determine the maximum shear stress in the shaft. And they gave us our G value of 10.8, 10 to the 3 KSI. So for equilibrium, let's draw a free body diagram. This diameter is 0.5 inches. This diameter is 1 inch. You have your torque here. This torque at D is 500 pound-force feet. So we have at TA and your torque at B. So equilibrium, you have your torque at A plus your torque at B minus the applied torque of 500 pound-force feet equals 0. Well, we have two unknowns in one equation. We cannot, it's statically indeterminate. Well, the problem statement said fixed ends. So we can do a compatibility condition that the angle of twist of D to A is equal to the angle of twist of D with respect to B. Go to a fresh page. So the angle of twist of D with respect to A equals the angle of twist of D with respect to B. This is due to being fixed ends. So, with that being said, for our angle of twist from D to A, we have to consider the change in diameter. The torque experience in this section is the same or consistent throughout AD, but the diameter in section AC is different than the diameter in section CD. So using our compatibility condition and our equation for angle of twist, this will be the torque in section AD, we'll just say TA, which we already said in our free body diagram. TA times the length, 5 inches, over J. This is a solid shaft, I should say. The diameter is 5 inches, so the radius is, diameter is 0.5 inches in this section, so the radius is 0.25 inches. So our polar moment of inertia is pi over 2 times 0.25 inches to the 4 times our G plus the angle of twist in the larger diameter region, which has a length of 8 inches. Notice how my units are all consistent. The polar moment of inertia in this region will be the radius corresponding to the diameter of 1 inch, so 0.5 inch radius to the 4 times G. And our compatibility condition is equal to our angle of twist of D with respect to B. So this is a consistent diameter part of the shaft. So we have our torque in this section, TB, times the length, 12 inches, over the polar moment of inertia, which is pi over 2 times 0.5 inches to the 4 times G. So if I multiply both sides by G and solve out the math division, you'll get TA times 1408 equals 192 times TB. So now we have this equation plus our equilibrium equation of TA plus TB minus 500 pound force feet equals 0. So let's rewrite it on the first page. You have TA times 1408 equals 192 TB. And you have your equilibrium equation, TA plus TB minus 500 pound force feet equals 0. So TA is equal to 500 pound force feet minus TB. And you plug this into here, and solve, you get TA is equal to 60 pound force feet, and TB is 440 pound force feet. Therefore, the maximum shear stress TC over J so for segment AC, the torque would be 60 pound force feet times 12 inches 1 foot times our outer radius, which is 0.25 inches, over our J, which is pi over 2 times 0.25 inches to the 4. This comes out to be 29.3 KSI. And for our maximum shear stress in segment DB, this comes out to be 440 pound force feet times 12 inches 1 foot to convert my units times my outer radius 0.5 inches over my polar moment of inertia so that'll be 26.9 KSI. So we'll end here for today. If there are any questions, please do not hesitate to send me an email. Please continue to work hard and be safe. Thank you.